we will discuss about the serial addition. So operation in the digital system or any digital computer are mostly done in a parallel way because this is a faster mode of operation. But in the serial operation, it require less equipment and it have a slow speed. Now we will see how to perform a serial mode of operation, and for that we design and see how a serial adder is designed and will operate or will implement. So earlier also we discussed about the binary parallel adder. So we saw there that the binary parallel adder have four full adder circuit, and in the single clock pulse we get addition. So to design a serial adder we need two shift register and one full adder circuit and one D flip-flop to store the previous carry bit. So we will see how to design it. So suppose we have two binary number defined or represented by A and B. So to store these values we must require two shift register. Suppose a shift register is represented by A. Shift register, it means that with every clock pulse a bit from a register A and B will come out. So two output is there represented by serial output. So in shift register we must have a common clock pulse represented by CP and a signal which indicate a shifting, that is shift right. This is common to both. And there must be a external input represented by SI. This is external input. So these two bits must be sent to a full adder circuit. In full adder circuit we have three input and two output represented by sum and carry bit. These two signal will given to full adder input. This is represented by X and Y, and the third input is the previous carry. So the previous carry, initially the carry bit must be in zero state or zero. So to store the previous carry bit, we will use a storage cell, that is a flip-flop. We will use a D flip-flop. So this is the block diagram of D flip-flop. Here we know there is an input D and there is an output Q, and there must be a clock pulse and a asynchronous clear input. So the C output is given to input of D flip-flop, and the output of D flip-flop is given to a full adder circuit. So we will give a clock pulse or the clock signal for D flip-flop also. So whenever the clock pulse, that is the CP input, is high and the shift right signal is high, then the signal or the clock of D flip-flop must be in active stage. These two signal will be and given to the clock pulse of D flip-flop. So one by one the summation bit or the sum bit is present in the full adder sum bit. So this sum bit can be stored in a register A again. So we can utilize the register shift register A. So there is a feedback signal here. This is SI. So this is the circuit of a serial adder. So we can see here then it use two 4-bit shift register and one full adder circuit and one D flip-flop and one AND gate. So one by one the bits from register A will come out and the bit from register B is come out and sent to the input side of full adder, and the previous carry bit is given to the full adder by D flip-flop, and the sum bit one by one will be present in the sum pin of full adder. So as long as the shift right signal here is high, the circuit will operate and perform addition operation, because as long as the shift right is high, then this clock pulse for the D flip-flop is high and it will save the previous bit or the previous carry bit. Now we can use a serial adder using a sequential logic process also. Suppose we have two register and there is two bits are stored, two 4 bits are stored in shift register A and B. So we have to find out the combinational circuit for next state of register. Shift register A and this is shift register B. Now we will find out the combinational part for finding the next stage of shift register. So for this we have to draw excitation table for serial adder. First, the input is present by, this is present state, this is next state Q, this is the output sum, and this is flip flop. Suppose we are using JK flip flop input J, Q and K, Q. So total combination here and present state and input is 8. So for carry bit, for some bit, the summation of 0 plus 0 plus 0 equal to 0, and here the carry bit or the next stage of flip flop is 0. This one is 1, this one is again 0, 0, 1, 1, 0, 0, 1, 1. The input for JK flip flop, is present state is 0 and the next stage is 0. Then the input combination, the excitation table of JK flip flop, we will see about the excitation table of JK flip flop. So this is Q, T plus 1, this is J and K. So if the present state and the next stage is 0, then the input is either no change, 0 0 and 0 1. So this is 0 fix here and this is don't care condition, 0 and don't care condition. If this one is 0, present state is 0 and the next stage is 1, then JK input can be either toggling 1 1 or 1 0. So it is 1 cross. This one is 1 0, then again either 0 1 or toggling, don't care and 1. If this is 1 1, then it is a no change condition, either 0 0 or 1 0. It is 1 0. So this is the excitation table of JK flip flop and we will fill the input of JK flip flop here accordingly this table. So if the present state and the next state is 0 0, then input must be 0 and don't care. Similarly, don't care 0 and the next stage is 1, that it is 1 and don't care. Similarly, this one cross 1, don't care, don't care, don't care and 0 0 0. So we can design our serial adder from this state table, excitation table. So the expression for S bit can be found out by using K-map. So we will draw a K-map for S bit. So input is either Q, X and Y. 0, 1, 0, 0, 0, 1, 1 and 1 0. So sum bit is high for this combination, this combination, this combination and this combination. So expression for S equal to, if we will simplify it, we can easily find out that it is x dash y dash q plus x y q plus x dash y q dash plus x y dash and q dash. So S equal to x XOR y q plus x XOR y q bar. So it is x XOR y XOR q. We can draw a serial ladder like there are two shift register A, shift register A and shift register B. So again there is a signal shift right. There is a clock pulse CP, two output here SO. It is represented by X and it is represented by Y. There is a XOR gate. This is some bit S and there is a JK flip flop. So this output and there is a clock pulse here also and JK flip flop. So we will find out the expression for J input and K input using K map again. And if we will find out then JA equal to XY and K input of JK flip flop equal to, so the input here, this is the K input of flip flop. So here there must be a clock pulse also in the JK flip flop. So whenever the clock pulse, this CP is high, and whenever the shift right input is high, then the clock for JK flip flop must be high, so it will operate. There must be a synchronous clear signal and the sum output or the output bit or the sum bit must be stored again in the register A, so there must be a feedback path between the terminal and A. So this is a complete diagram of or the complete circuit diagram of serial ladder.